Let's look at some homework hints for homework number 3. So I'm going to try to get you started on these without giving a ton of information away so that you wouldn't have a lot of fun solving it. I know you wouldn't like that. So let's look at the first one. The first one, we have water going down a horizontal pipe. And you can tell that this pipe is, let me get my pen here, it's flowing in one end and out the other end. Mind the squiggly lines here. So easy to draw with these pens. So anyway, remember these from the PowerPoint and from chapter 3. We have S, the tangential part of the streamline, and we have the normal part. So in this case, S is pretty much the same as X. So we can align our coordinate system this way as we did, and we can say that S and X are pretty much the same thing. So if that's the case, then we have ourselves moving along the streamline. X is the same as S, and the equation of motion along a streamline is given by gamma times the sine theta minus sine here, minus the change in pressure along S. That will be equal to velocity times the change in velocity along the tangent. So keep in mind in this case, the tube is horizontal, so you can just forget about that sine term because theta here is equal to 0. So once you do that, you'll end up with an equation over here, and you'll have to work on that and integrate it from one end of the pipe to the other, and you should be able to get part 1. Now the second part is a simple application of the Bernoulli equation, so I won't give you too many hints on that. You should be able to figure that one out. But the first part's a little tougher. Actually, you use some integral calculus to get from here to an expression for the pressure across the system. Number 2 is a manometer. On this one, I put the wrong figure on the homework. Sorry about that. So here's the correct figure. It's got a pedostatic tube, and you've got that to measure airspeed, and you're getting a difference in height in the manometer, as you tend to do, because remember the velocity comes in here at some speed, and then it hits this point right here, which we call the stagnation point. So that stagnation point is going to cause this delta H basically across here. So in this one, just a little bit interesting to try to, excuse me, to see what kind of deviation can be detected for air flowing at 50 meters per second, and then repeat that flow for that calculation for 5 feet per second. So you're basically going to do the same problem twice here for the 2 different velocities. And we're going to look at this error term, which they've given you for each result. Basically, which one causes more error in a percent basis. So take a percent, take the value for the 0.02 inches in this, pretending like you could only maybe read it plus or minus 0.002 inches. So it's a little bit like a lab exercise where you're just going to try to see how precise this thing is. So number 3 is pretty easy. That's just a straightforward Bernoulli problem, so I didn't give you too many hints on that one. On number 4, you've got water siphoning down a tank, and you've got to figure out the pressures all along through here. So it's another Bernoulli problem. And then kind of in a new twist, energy in the hydraulic grade line, which we mentioned in the PowerPoint slides and is in sort of near the end of chapter 3. It's not very hard, and if you look at that section in there, I believe it's, section 3.7. You can look at the energy line. So Bernoulli problem, lots of points. Start from the ends because that's where you know the most. Remember here and here you have atmospheric pressure, so those are good places to start. And then work your way inward. Once you have the pressures at all these points, and there's 1, 2, 3, 4, 5 points. If you have that information at all 3 points, you can come up with the energy grade line and the hydraulic grade. So you'll basically make a figure similar to figure 3.23, only it'll be a figure for your siphon, not for their device in the book. And lastly, the mini design problem. This is kind of an interesting one. Remember, this is open-ended, but what we're looking for here is just a design equation. So there's no numerical answer here. So your problem should just come up with an equation. And you're looking at using Bernoulli's and continuity. So they build the design equation from those. So that's a good big hint. So your design, the biggest hint here is that your design needs to work under the most demanding case. So I believe this is a 3-story problem. You've got the ground floor and 2 floors above it. So the most demanding case is when all faucets are open at one time, right? So you've got to have a system that can deliver water. You don't want a system where the guy on the top floor opens his faucet and the next guy down can't get water because it's all going to the top floor. It's got to have enough pressure to deliver in the most demanding case. So there you have it. Remember, use these equations here to come up with a design equation. So a design equation would make it easy for you to try different diameters and different pressures and see if the system would work or not. So that's about it for this one.